All right. Thank you, Yuta, for the kind introduction. So, just an announcement that we're going to shift the schedule around this morning a little bit. We're going to move most things. This talk will be 60 minutes instead of 90 minutes, unless I run over, but it's planned for 60 minutes. And then that will leave some time for another problem-solving session at the end of the morning, right before we leave for the excursion. So okay. You need notes, apparently. Okay. So I'll talk about, so I'll start. I'll talk about gap mechanisms and differential privacy. Okay, so far a key concept in a lot of the lectures we've seen has been this notion of sensitivity, or what I will, for sort of emphasis, call the global sensitivity of a function. So we're looking at either releasing the value of a function that has low global sensitivity, as with the Laplace mechanism, or perhaps optimizing over a vector of query functions, each of which has low sensitivity, as with the exponential mechanism and the report noisy max mechanism that Katrina mentioned. The sensitivity can be measured in various norms. So generally, we talked about the L1 norm on a vector. It turns out it makes sense to use the L2 norm in some cases. That's also fine for appropriate noise addition. In the case of releasing many counting queries, a vector of counting queries, the right norm is the L infinity norm. But in any case, it's some norm on this vector that you're asking how much, what's the maximum possible change in that norm of the vector. Okay, but the motivating question for this morning's lecture is what do we do when the sensitivity is not the same everywhere, when we get this when we get inputs that, we get a problem where without a sort of uniform bound on sensitivity. And we'll see that there are still interesting things one can do. We can take the answer to this question in a variety of different directions. I'll be pursuing one of them this morning. But the sort of motivating question to have in mind is how we can have higher accuracy on instances where the sensitivity is lower. And another technical point that'll come up is so far we've seen this sort of pure epsilon zero notion of differential privacy. We've seen something called concentrated differential privacy that Kobe at least mentioned, which is a superset of differential privacy and epsilon delta differential privacy. And one of the things that will come up this morning is sort of some further, the types of mechanisms I'll be talking about illustrate some further differences between these definitions. We'll be way out here in the blue region dealing with mechanisms that have no analog in these sort of smaller, more restricted notions. Okay, so this is a Laplace mechanism. Just a reminder, remember we've got some measure of how sensitive our function is. Normally, we look at it in the L1 norm, looking at how x and x, how much the function can change over neighboring data sets. And this is some measure of the sensitivity of the function. What we know is that we can add noise proportional to this global sensitivity to each of the entries of the function to satisfy differential privacy. Okay, so global sensitivity is this notion. It's worst case over all possible inputs. It's taken over all possible pairs of inputs x and x prime. In fact, it sometimes makes sense to look at more local notions of sensitivity, and I won't be working with this too much, but this sometimes comes up, and it's sort of a useful concept to have a name for a few reasons. But here we're going to sort of look at this, not the sensitivity over the entire domain of the function, but in the neighborhood of a particular database x, and this is just the maximum over x prime, which are neighbors of x, of the variation of the function, let's say an L1 norm or an L2 norm or whatever it is. Okay, so the global sensitivity is just the maximum of this local sensitivity over all possible functions, over all possible inputs. And starting around the time of the original paper on differential privacy, there were a variety of techniques introduced to try and add, release the value of a function with error or distortion, somehow scaling with this local sensitivity. It turns out it's not that easy. I mean, you can't you can't always get that, but under certain extra conditions you can. Okay, and this will come up more explicitly when I talk about analyzing network data on whenever that is, on Thursday, I guess. Okay, but today I'd like to talk about sort of I'd like to start with a rather extreme version of this, of a function that has big differences in how it varies locally. And a nice function to have in mind would be a function that is sort of piecewise constant. So imagine that I've got, here's my big domain, these are all possible data sets, and it's been chopped up into pieces, and and these pieces are the pre-images of the function f. So, or possible pre-images under f of various points in the image. And so if we imagine a function that is constant on each of these pre-images, then it's going to have very high sensitivity when it's local sensitivity when you're right at the boundary between two pre-image sets. But inside any of the pre-images, it has local sensitivity 0. If I'm away from the boundary, then changing the value of the data, changing one person's data doesn't change the value of the function at all. Okay, and a good poster child for this sort of type of function is the mode function. So suppose I'm given a data set, it's just a list of values in this domain X, and we want to return the most frequent value in the data set. Okay? So breaking ties, say, lexicographically. Okay. So if for example, no value appears more than once, then this function is very sensitive, it's not very well defined. But if you've got like a nice clear mode on your data set, like for example with this data set here, which is generated from taking the histogram of a mixture of two Gaussians, then in fact you get a very clear mode. And in this particular data set, you'd have to change lots of data points for the mode to change. Okay, so not only are you not only does changing one point not change the mode, but actually changing many different points. You'd have to change about 80 points on this particular data set for the value of the mode to actually, shift. Okay, and right. So there's our mode. Okay, so suppose we're interested in releasing the mode of our distribution, subject to differential privacy. Okay, we could ask, well, what is the sensitivity of something like the mode? And can we add noise to the mode? It doesn't really make sense because unless we've got like a particular metric on the output space or something like that, it doesn't necessarily make sense to add add noise to the mode. And in fact, the example that Katrina gave in her talk of finding the page on Facebook with the most likes or something like that, sort of, again, you could ask, even if each person only got to vote to like one Facebook page, right? You could ask to sort of release that most liked Facebook page. That would be the mode of a data set, and it wouldn't make sense to add noise to the name of the page. Okay, so suppose we want to do this. What kind of things can we do? Well, one kind of thing we could do is to release the entire, to just rather, instead of thinking of the releasing the mode, just think of releasing the entire histogram of the data set, right? So if I think of releasing just, imagine my data set is sort of consists of a certain number of copies of different possible values, and I just want to say, well, for every possible value in the domain, I'm going to release, I'm going to add noise 1 over epsilon to each of the values, and I'll just release that vector of noisy counts, right? And because remember that for the entire histogram, the sensitivity is 1 in the L1 norm. I can release the entire histogram with noise only, adding noise, Laplace noise on the order of 1 over epsilon for each entry. And that'll satisfy our definition of differential privacy. And then, for example, I might report the, an estimate of the mode as just the entry of the histogram with the largest noisy value, and that'll work pretty well. Okay, we could also use report noisy max, this, or the exponential mechanism. And in this particular case, for the particular, for the case of releasing the mode, if all we're going, it turns out to be the same thing. So report noisy max is exactly just adding noise to the histogram and outputting the name of the thing with the highest noisy value. Okay, so these are two natural mechanisms for releasing the mode, and it turns out they're essentially the same, and they have the following performance guarantee. They have the following sort of accuracy guarantee, which is that if I want to, whatever the value mode hat that I release is, I don't know that it'll necessarily be the exact mode because differentially private algorithms can't be deterministic. So it won't necessarily be the exact mode for all data sets. But what I can say is that it'll have, its count will be pretty close to the count of the actual mode, right? So whatever I release will have count about at least the count of the actual mode minus an error term, which is about log d over epsilon. And the term I want you to notice is this log d. Okay. So where does the log d come from? This is the fact that what I'm actually doing is I'm adding noise to each of the counts in this histogram. So each of them individually has standard deviation about 1 over epsilon, but just by because there are d different counts, there's a reasonable probability that one of them will be quite a bit larger. And if you just exactly the same sort of examples that came up in the analysis of the exponential mechanism will work here. So if you had a data set where there were lots of elements whose counts were almost the same as that of the mode, then you'd get an error of about log d over epsilon in your estimation, meaning you'd be likely to, in a data set where the inputs look like the red dotted line, you'd actually be reasonably likely to produce one of the other inputs, not the mode itself. And so you can argue just by a tail bound that you're going to get about this log d term, and it turns out that that term is unavoidable for this particular mechanism. Okay, so that's fine. This is a pretty, most of the time this is a pretty good guarantee. For example, log d seems like a pretty small quantity, and so maybe we're happy with this. But the problem is that we're getting this dependency on this parameter that we don't necessarily know how big it's going to be. So if we're in a setting where this dimension, the number of possible values that the mode could take on, the number of possible values in the data set is very large, then then we might be getting sort of an unacceptably large error here. And the thing we're outputting, it's sort of in an extreme case, is when log of d is bigger than n, when the domain size is super exponential in the actual size of the data set, and then this utility guarantee would actually become meaningless. Okay, so we could try a different approach, which is to say, well, coming back to the sort of our intuition about sensitivity and things, on this particular data set, again, the mode seems to be very, very well defined, right? So we'd have to choose a lot of data points, we'd have to change a lot of data points for the mode to change. And so it feels like even if the domain were very large, even if we're in this sort of exponentially large, living in this exponentially large space, we should be able to release, it feels intuitively like we should be able to release the mode without releasing too much information about any one individual. Okay. And so one way to sort of formalize this a little bit is to ask, well, how many, how can I sort of pin down the number of data points I would need to change in the data set in order for the answer to my function to actually change? Okay, so in this case, that's going to be exactly the difference between the count of the most frequent item and the count of the second most frequent item. Right? That's how many things I would have to change in order to shift the mode from this most frequent item to the next most frequent item. Okay, we'll call that function dist of x, for dist for distance. And we can ask, well, how sensitive, sorry, there's a typo here, this should be, how sensitive is this distance function? Well, this distance function is the difference of two different counts. And if I add or remove a point from the data set, I can only change one of these two counts, and I can change it by at most one. And so the distance itself, this distance function, has very low sensitivity. It has sensitivity at most 1. Okay? And that's sort of a general phenomenon. If you take any subset that, in this case, we're looking at subsets of data sets, and we're looking at, what's the distance between the data set we have and sort of the boundary of the preimage it lives in. And this type of function, what is where I'm asking for the distance between my data set and some other set of data sets, some collection of data sets, that function is always going to have global sensitivity at most 1, because I can only change distances by 1 when I move the data set by 1. Okay, and so one thing we can definitely release while satisfying differential privacy is a good approximation to this distance. So even though it's not clear we can release the mode, we can certainly release the distance, and then there's no dependency. When I'm talking about releasing the distance, there's no dependency on the size of the universe I'm living in. Okay, so sorry, that was a version of that picture. Okay, so let's consider the following idea for releasing this mode function. So again, my distance, dist x, is the Hamming distance to the nearest data bits with a different mode, so that's max x minus second max x. And I'm going to do the following thing. The first thing I'm going to do is I'll compute an approximation to this distance function. And I'm then going to apply some test to decide whether or not it's okay to release the mode. Okay? So if this noisy distance d tilde that I just computed is sufficiently large, larger than about 1 over epsilon, then I'll return d tilde itself. And along with d tilde, I will also hand out the exact mode of the data set, this deterministic function. Okay? On the other hand, if d tilde is too small, then I'll return d tilde and a special symbol saying d tilde was too small. So notice that in this algorithm, there's no dependency on sort of the size of the domain my data lives in, right? So the only thing that's kind of going to play a role is how far I am from the nearest data set where the mode has changed. Okay. And so it turns out that this algorithm is actually differentially private. And something that's a little easier to see is that it will actually behave well when the difference, this gap between the most frequent item and the next most frequent item is sufficiently large. Yeah?
The assumption here is that if the distance is small, then I won't get the exact mode. And if I don't get the exact mode, then I may as well just get an error because it's incorrect anyway. But that's actually not true. I may say that, well, if there are two things that are close together, I don't mind which one you give me. It still gives me the information I'm looking for.
Right. So there are sort of a couple of things here. So I'm not claiming this is the best algorithm to, the best way to release the mode. I just want to, what I want to show you is that we're going to analyze this algorithm. We'll actually see a better one not momentarily, but in relatively short order. But what I do want to kind of claim that it's not a crazy thing to do. And it has this feature that it has, we've sort of thrown away the dependency on the domain size. Okay. So, where would this be? Let me, just just to give an example of where this might be useful, imagine that my data set, you know, let's say I know it's normal with standard deviation. I know my data, I think my data set, my data is normal with standard deviation about 1, and it's, but I just don't know like where on the real line it is, okay? And I want to figure out where it is on the real line. So then I might plausibly just sort of divide the real line into bins of width about, you know, I don't know, 10 sigma or something like that, so that my data points are likely to mostly fall into a single bin. But I've got infinitely many bins that the data could fall in, right? So any mechanism that has a dependency on the number of bins I'm considering is going to fail miserably in that setting. Whereas this mechanism will actually work fine. So I'm going to prove to you in a second. We'll prove that it's differentially private in a second. But the statement that's maybe a little easier to see is that if the distance from the nearest data set with a different mode is sufficiently large, if it's bigger than, let's say, t times epsilon, then with high probability, this algorithm is actually going to release the correct mode. I think I have 1 minus epsilon, e to the minus t. There's a term missing here, but it behaves roughly like this. And you know, that's just because if dist of x is really big, then if dist of x is really big, then d tilde is very likely to also be big, right? And so you're likely to pass the test. Okay, so as long as this distance is sufficiently large, then I'll actually release the mode with high probability, the exact mode. And this comes with an additional nice benefit, is that when I do release the mode, the user who's on the other end knows they're getting the exact mode. They know that there's no error in that component. Okay, so let's just try to explain why it's differentially private. So what's going on now? So let's fix, So let's fix two data sets, x and x prime, that are neighbors. And it's useful to have in mind this picture of the preimages of the function. So here's x out here, and here's x prime. Okay? And so the first case to consider, we're actually going to consider two separate cases, and the first case looks like this. Okay, so the first case is where x and where mode of x equals the mode of x prime. Okay, and then, so in this case, what are we looking at? We're looking at, if we go back one slide, if we look at our mechanism again, what are the possible outputs? The possible outputs are d tilde and the exact mode of x. Or if the data set is d prime, it's, you know, d tilde and the exact mode of x prime. Or d tilde and perp, right? And so, so I'm sort of considering sort of the possible outputs on possible outputs on input x and on input x prime. And the first thing I'd like to, I want to point out is that actually in both, no matter what the algorithm actually outputs, the output is sort of a function of this pair, the d tilde and the mode, right? Because the decision whether or not to actually release the mode is only a function of d tilde. So basically, as long as this pair doesn't release, this pair doesn't really, as long as seeing this pair doesn't help me distinguish the two data sets, then in fact, seeing the output of the algorithm isn't going to help me. Okay, and the second thing to observe is that because the second components of this vector are the same, all that we really care about, the only way we could distinguish these two pairs is if there's is based on the difference in the distribution of d tilde under x and d tilde under x prime, and because those two distances are going to differ by at most 1, whatever they are, the distribution on d tilde under x is going to be epsilon indistinguishable from the distribution of d tilde under x prime. And I'll just use this shorthand where we'll say if I've got two distributions p and q, we'll say they're epsilon indistinguishable if they satisfy the definition of the kind of condition that's defines differential privacy, meaning that for every possible output there, I should use different symbols.
I need to say the distance function which you already proved was, or you say
Right, no, I just want to, I'm just nailing down this notation that I want to use. But yeah, so basically, why are these two indistinguishable? That's just the Laplace mechanism. Okay, so in the case where they happen to both have the same mode, then we're basically just releasing sort of any leakage comes from is passing through the Laplace mechanism, and we already know how to analyze that. The second case is where they're actually sort of on either side of when their modes differ. Okay, and in that case, in that case, what's going to happen is that what can I say about the distance of x, dist of x in that case? Right? So if their modes differ, then the distance to the nearest data set where the mode is different is, well, at most 1, right? I mean, it's exactly 1. And the same is going to be true with dist of x prime. They're both going to be equal to 1. And therefore, what's going to happen if we sort of look at just how the structure of the algorithm, this dist of x is going to be very small. I'm adding a relatively small amount of noise to it. And I've picked the threshold on d tilde precisely so that the probability of exceeding the threshold is delta. Okay, so in that case, what's going to happen is that the probability that we release the mode is at most delta. Okay, and so in this case, the outputs A of x and A of x prime are indistinguishable, sort of epsilon, satisfy the conditions of epsilon delta differential privacy. In fact, with epsilon equals 0 and this parameter delta, and that's because because dist is the same in both cases. The first component of this vector isn't going to leak any of first component of the output isn't going to leak any information at all. The only way the output can help you distinguish x and x prime is if the noise happens to be too large, and in that case, you'll of course be able to distinguish them perfectly, but that happens with probability at most delta. Okay. So this is the whole proof, and what it sort of this proof really kind of gives us a stark case of this interpretation of epsilon delta privacy as something where there's this possibly very bad event that happens with probability delta, in which case at most delta, in which case you can distinguish x and x prime, but the rest of the time you're basically satisfying epsilon 0 differential privacy. Okay. Any questions about just this argument, sort of how to break down these cases? Okay, so this sort of general approach works for any function f that's sort of piecewise constant in this way, that you can release f of x, the value of f of x exactly. You can release it as a deterministically, as long as your input x is sufficiently far from an input with a different answer. Okay, and this works regardless of the domain size. And that's sort of the important feature of this this type of mechanism. And it's a special case of this algorithm that we just saw is a special case of a more general principle, which is sort of called I guess called the proposed test release framework. It was formulated by Dwork and Lay in 2009. And again, sort of what they imagined is sort of, rather than just decomposing the function into pieces, imagine we decompose the domain. Imagine we've got some algorithm B, and we can somehow break the domain into pieces such that within each piece, if you've got two data sets that are both within the same piece, then they satisfy the conditions of epsilon delta differential privacy for the algorithm. So it's not going to be it's not going to be easy to tell them apart, to tell apart x and x prime based on the output of B. Then you can sort of do this thresholding idea generally, and what you do is if you can somehow check whether or not you're close to a place where the algorithm has problems, then you can actually, again, if you can do that check differentially privately, then you can first test whether or not you're in a sort of a safe region for the algorithm and then run the algorithm. Okay. And the test doesn't actually have to look like this. In fact, the framework is a little more general than that. There's just you just need some test algorithm that that will reject with high probability if x is near the boundary. Doesn't have to be exactly like this one. Yeah.
So mathematically, I know the answer, but just intuitively, I don't.
Right.
So if we know that these things compose, right? So you can now look at group privacy. But this sort of intuitively, like if I now add a large group, and I know all about that group that I'm adding, they change the mode. Why? Like,
right. So okay. So why does this not sort of contradict? So okay. So this is a class of mechanisms that is not epsilon zero differentially private, and it doesn't satisfy this concentrated differential privacy either that Kobe was talking about. It's really epsilon delta. And so group privacy normally says if I'm considering two data sets X and Y that are possibly a little further apart, then the further apart they are, the sort of weaker and weaker my privacy guarantee gets. Epsilon delta differential privacy, if you look at sort of the group privacy guarantee, it drops to 0 around when this distance gets to be around log of 1 over delta over epsilon. So for groups, do I have that right? I think that's right. Yeah. So once this distance exceeds about log 1 over delta over epsilon, I mean, there are constants. There's a constant there, but like ish. Then your group privacy guarantee becomes meaningless, and this mechanism sort of exhibits that starkly.
If I can quickly iterate, so this is
yeah.
why this very problem would have a lower bound for epsilon 0 from this packing argument, which would explain the fact that for epsilon 0 you do get this group privacy.
Yeah, that's an excellent point. I actually have a slide on it right at the end of the talk, but it's not a very good slide, so let's say it now. These types of mechanisms sort of exhibit a resistance to these packing arguments and more generally to information theoretic arguments. So another thing that this mechanism exhibits is that the mode mechanism sort of illustrates this nicely. In fact, this proposition is the whole story. So remember, this says if you have a clear mode, then you can release it with high probability. So in particular, if all your data set, if there's only like one value in the data set that appears n times, I will tell you that value. Okay. What that means is that I can find a distribution on data sets such the mutual information between the input and the output of this data set, the input and the output of this process is at least about log d. In fact, I can do a little better than that. I can get like almost n times log d. The important thing about log d is it's not bounded. It's not bounded by just functions of epsilon and delta. Okay, and so that means that all these sort of proof techniques that are going to be based on packing arguments, including ones we'll see later today for local differential privacy, are going to break down. Okay? And that's why we need sort of much more sophisticated proof techniques for handling epsilon delta. Look. Okay, so let's actually look at just an application of this, just this mode algorithm, just to kind of get our develop some further intuition for it, and then we'll try and generalize it a little more and look at a different variant on it. Okay, so so let's look at an application. We're going to look at a property called sampling stability, or stability under subsampling. So something that comes up a lot in machine learning and various other fields, if you're trying to design, if you've got a function you want to compute and you're trying to design a version that's somehow robust to noise, is to do something that's sometimes called bootstrapping. It's sometimes called ransack in the vision literature. But the idea is you're going to take some function you care about, and you're going to compare it. You're going to compute it on a bunch of random subsamples from your data set, and then you're going to somehow aggregate the values you see. You see like a bunch of different values for the function, and maybe you take the median value you've seen or some other kind of, maybe the average value you see. You take some sort of aggregation of those values. Okay. And basically what we're going to see is that sort of this idea plays well with differential privacy, and we can use it to design a differentially private algorithm. So just to formalize things a little more, given a probability, number p between 0 and 1, a p subsample from X is just my shorthand for a uniformly random subset of X consisting of Pn points. Okay, let's assume that Pn is an integer. Okay, and we'll say a function is p subsampling stable on a data set X if there exists some value such that when you take a random subsample of size p times n, you evaluate f on that subsample, you will get this value with like some strict majority of the time. Let's say 2/3 of the time. There's nothing magic about the number 2/3. Okay. So this is a particular type of stability, right? It basically says that if you take a bunch of subsamples from your data set and compute your function f, a strict majority of the time you'll see there's one value that'll come up, a huge fraction of the time. So how could we achieve exploit that? Well, what we could do is take some differentially private algorithm A and somehow transform it into a different differentially private algorithm. So far, this particular transformation is not sort of specific to is not specific to these like stability-based mechanisms. It's actually a very general thing. But what I'll do is I'll take my data set X and I'll randomly take k subsamples, each of which contains a p fraction of the data set. Okay, so I'll sort of repeat the following operation k times. I'll take a random subsample of p times n p times n points, collect those, take another random subsample, take another random subsample, another random subsample. Okay. And then what I'll do is I can compute my function on each of these subsamples, and these will give me values z1, z2, z3, up to zk. Sorry about that. And and then what I can do is I can feed those to the algorithm A, and now I need to design an algorithm A that takes the z values, takes the possible outputs of the function, takes a collection of k of them, and produces some output. And there's sort of a general lemma that says that if you run this process, then what you'll get, the overall algorithm will be differentially private, and the parameters will be inflated by a factor of about k times p. Okay? So in particular, if k is 1 over p, then you get back another epsilon delta differentially private algorithm. Okay? And if k is less than 1 over p, then you get back something better than that. All right, so so I'm not going to prove this statement formally, but in the case where it's particularly easy to see when in the case where k is 1 over p and I choose the samples so they're disjoint, then if I change one entry of x, it's going to change only one of these samples. Let's say this one. And that means it's going to affect only one of the inputs to A. And because A is epsilon delta differentially private, that means the output distribution won't shift very much. Okay, so this is sort of a general transformation that lets us take algorithms for aggregating outputs and apply them to functions that behave well under subsampling. And in particular, if A is the mode function, the algorithm for the mode that we were discussing earlier, then if I've got a value of z that appears many times in the outputs, then it will come up. It will be the thing output by A. Okay. So basically, this algorithm will give us the following statement: if f is p subsampling stable on x, and p is less than about 1 over epsilon, then you can sort of set things up so that when you run this you run this sort of sample and aggregate thing I had on the previous slide, you'll actually get this value z with essentially overwhelming probability. Okay, so with very high probability, and that's simply because that there's this value z star will appear a majority, will be like a clear majority, a clear mode in the inputs to A. Okay, so that was sort of an application of this mode function and of this sort of stability framework. Okay, so let's come back to our sort of our example we had before. Here's our data set. As Yuta was saying, like I don't normally care just about the mode. First of all, I want to know the mode. I want to know some. When I want to know the mode, it's not because I care about the exact mode. I just want to know, values that come up often in the data set. And what I'd ideally like is to get, in fact, the whole histogram, not just the mode, right? And so again, I'm going to think about my histogram as sort of a bunch of bins that contain very different numbers of data points. And what I want is for every possible bin, of which there are d, I want the count, the number of points that lie in that bin. Okay? And as we were saying before, one thing we can do is we could just add noise on the order of 1 over epsilon to each of these counts and release the counts of and release this sort of long vector of noisy counts. Okay. And the problem with this is that there are two problems. One is that this generates a huge output. If d is very large, I'm somehow, I really only care about the bins with non-zero counts, but somehow I'm given this huge vector. But in fact, sort of, it's a little more. The problem goes deeper than that. So one thing I could do is just, keep only those bins, those counts that are sufficiently large. I could pick some threshold tau and keep only the counts that are above the threshold. But the problem in that case is the sort of more fundamental problem will come through here, which is if the domain is very large, if my data set actually looks like this bottom picture, then what I'm going to get is after I add noise, just because of random variation, there are going to be lots of bins, even the bins that were empty before, that will suddenly appear to have a large count just due to the randomness in the Laplace noise. Okay? And in particular, if the log of d, if the log of my domain size exceeds n, then I'll I'll get more noise than signal. Basically, I'll get tons and tons of spurious bins, and almost the fraction of counts that I see that are actually belong to bins that actually contain lots of points will be a negligible fraction of the output. And this problem for epsilon 0 differential privacy, this problem is unavoidable. Okay, this dependency on log D we can't get away from, unfortunately. But with epsilon delta we can, and we're going to see how. Okay. So I forgot the attribution on this slide. Kobe, can you remind me which paper this comes from?
That's BNS 15, I guess.
Sorry. Okay. This is from a paper of by Melnisheim and Stemmer. So here's what we're going to do. We've got this algorithm A of x. And for all bins with non-zero counts, what we'll do is we will compute the number of points in the bin, add Laplace noise, and we will get this sort of noisy count, but we'll only do this for bins that actually have points in them. So even, for example, if our data lie on the real line and we have infinitely many bins, we're not going to worry about all the infinitely many empty bins. We're just going to worry about the bins where the points actually show up. But this is important. If we just return the noisy counts for, if we returned the noisy counts for all the bins with a non-zero number of points in them, then this would not be algorithm wouldn't be differentially private, and that's because it would actually tell you whether or not a bin is non-zero, has a non-zero number of data points in it, right? And so it would tell you the support of the data set, and that support itself reveals a lot of information. In particular, if you add a new point which is all alone in its bin, suddenly you'll see that bin showing up in the output. Okay. So the solution to that is to truncate, to return only those bins with sufficiently high noisy counts. Okay, where tau is this sort of magic number we had before, log 1 over delta all over epsilon. Okay. So again, this is epsilon delta differentially private, and I'll prove that in a second, but maybe the more the more interesting thing to observe is that this is actually a really good way to release the histogram. Okay, because what it tells you is that you're going to add noise 1 over epsilon for all the points that actually do occur in the data set. You'll add noise 1 over epsilon to their counts. Okay, and so the error you'll get in those counts is about the maximum error you'll get over those bins is going to be at most about log n over epsilon, and that's because there are at most n different bins that are there are at most n different bins that have a non-zero count in them. So there I'll get error about log n over epsilon. And on the other hand, all these empty bins out here, I'm just ignoring, and the bins that are actually going to cause me the largest problem for accuracy are those that are sort of below this threshold tau, those that have very few data points in them. And there my accuracy is going to be about log 1 over delta over epsilon. And that's just because, for those I'll report their, even if they have a non-zero number, even if they have a single data point in them, with high probability, I'll report them as absent from the data set. And so on those bins, I'll be off in my estimation by about log 1 over delta over epsilon. Okay, so so this gives us a way to analyze, to report essentially all the large bins. And this addresses Yuta's question of earlier, is like what happens if I've got two values that are both two bins that have lots of points in them. So I've got sort of, I don't have a well-defined mode, but both of them are large. Then I'll report both of those bins along with counts for those bins accurately. Okay, and why is this differentially private? So here the picture, so remember I had this picture earlier that we had sort of different preimages for the function. And this picture here in this case is not is not particularly represented, isn't quite right, because here the sort of, in some sense, the thing you're really releasing with this type of mechanism is sort of the names of the bins with lots of points in them. That's really the information you're after. Like once you have the names of the bins, you could run a second query just on those bins to get approximate counts. So sort of the interesting thing you're releasing here is the support, or some approximate version of the support of the distribution. And the cool thing is that this algorithm will give you useful output even if the exact support is highly sensitive. So even if you have lots of bins that just have 1 or 2 data points in them, this algorithm will still produce useful output. It just won't give you those bins. It won't give you those sort of sensitive bins. So this picture, for this mechanism, this picture is a little too simplistic. It doesn't quite capture geometrically what's going on, although it's not a bad intuition to have in your head. But the way the reason this is epsilon, or the way we can see that this is epsilon differentially private, epsilon delta differentially private, is to notice that actually we're running in some sense what we're doing for each bin, and there might be, there D could be arbitrarily large or even infinite, but we're basically running D independent copies of the same mechanism, of a simpler mechanism. Okay, and so the observation that helps us analyze what's going on here is that once we fix x, once the counts n sub j are determined, then essentially what I'm doing is I'm just conditioned on x. The action of this algorithm on each of the bins is completely independent. And really what we're doing is we're running some like little function that takes an integer m, and if m is equal to 0, it returns 0. And otherwise, it sets m tilde to be m plus Laplace noise, and then it thresholds that thing. So then it returns 0 if m tilde is less than this threshold tau, and it returns m tilde otherwise. Okay. And this algorithm, so this is the algorithm we're implicitly running on every bin, each of the possibly infinitely many bins. And we're running this algorithm sort of in parallel. And this algorithm, this really is a special case of this stability, of this framework I had before. I'm sorry if my handwriting is hard to read. You guys can ask questions. Or, yeah. Is my handwriting legible? Yeah. Okay. I mean, it looks fine to me. But yeah. All right. Okay. So so we're running like D copies of this simple algorithm in parallel. This simple algorithm is epsilon differentially private. And now if I go back to the sort of the whole algorithm, any one person, their data affects only one bin. And so it's sort of, even though we're running many copies of this simple mechanism in parallel, any one person affects only one of those copies. And so as long as they're collectively, as long as they are each individually epsilon differentially private, then collectively they are epsilon differentially private, right? So this is the sort of second key observation, is that each person in each data point affects exactly one copy of B. Okay. And this same type of mechanism can be, this type of reasoning can be generalized, for example, to other settings where, for example, a setting where each person gets to affect at most, L bins, where L is some bound that's much less than N, something like that. Okay. So, and also if we plug this truncated histogram into the sample and aggregate framework I had earlier, again, we'll get a slightly more interesting statement, which is that we can sort of get almost the same type of statement we had before, but whereas before, when we were using the mode function, we needed our subsampling process to return a particular value a strict majority of the time. Now it just needs to return a particular value sufficiently frequently. So for example, if it returns at a constant fraction of the time, that's good enough. It doesn't even have to be a constant. It just has to be enough that it shows up with sufficient frequency in the histogram after you do the subsampling process. Okay, so again, we get sort of a more general version of the subsampling result. Okay, so those were the examples I wanted to give you of this type of reasoning in differential privacy. It turns out this reasoning is useful for a number of other problems, and maybe I'll take a second to say I'll say a little bit about that. But just coming back to this point that came up earlier with John's comment and one of the questions, that one of the interesting things about this gap-based histogram, and the mode is sufficient for this also, is that you can have very high mutual information between the input data set and the output. Okay, and this is you cannot get this with epsilon 0. So for example, with epsilon 0 differential privacy, the mutual information between the input and output is bounded by epsilon times n. In fact, it's more like epsilon squared times n, but who cares? The point is it's bounded by some quantity that doesn't depend on the domain size. It just depends on epsilon and n. Okay. Whereas here, in general, with epsilon delta differential privacy, you can have sort of unbounded mutual information. I forget who the first person to point this out was, but certainly it came up in this a paper of Anindya Day on proving lower bounds. But this unfortunately also sort of highlights why these packing arguments, John didn't present them this way, but under the hood they are information theoretic arguments, basically limiting the amount, exploiting the fact that an epsilon 0 differentially private algorithm can reveal only a small number of bits of information about its input. Okay. And then, okay, so as I said, these sort of gap-based mechanisms, these ideas can be applied to a variety of problems. There's sort of a version of the exponential mechanism that also where you can also get away from the dependency on the domain side, although there you need a gap again, sort of like what we had for the mode. You need sort of this version of the exponential mechanism requires that sort of you're optimizing over a bunch of functions, and there has to be some separation between the biggest functions and the other functions. It has some applications in learning theory. In fact, that's where it was originally designed. It has some applications for releasing robust statistics. That's what the way it came up in this paper of Dwork and Lay I cited earlier. But the basic idea is of all these algorithms is somehow to try and understand the conditions under which the output of the algorithm will actually be stable, and then test for those conditions explicitly, but in a way that is differentially privately, right? Test for those conditions differentially privately. Okay. So I think I'll stop there. So yeah, thank you.